So yesterday we did two examples, one for freeway, the other one for multi-highways, and these examples were for what? What did we calculate? Level of service. And the calculations in which you calculate the level of service, we call it what? Operational analysis. Okay. Now we are moving on to something which we call as the design analysis, and I explained earlier as well. In design analysis, we are trying to find out what? Number of links. Okay, so it's a new freeway, obviously. Don't design the old one, right? So it's a new freeway, rural area. Like I did yesterday, let me write down this data because we will be moving up and down. Okay, so freeway, rural area, DDHP is given, and as I mentioned earlier that all these things happen for each direction. Peak hour factor, they are familiar users, %, trucks, and they are saving heavy mix. And what does heavy mix mean? It is written there. Okay. So SUT is what? And the TT is trailer truck. Okay. What is the normal mix? This is heavy mix. 30% SUT, 70% TT.
50%.
What is the normal one?
50%.
The opposite.
7.
Okay. TRD. Okay. We have level terrain, a long segment on a level terrain. But there is a 2-mile segment of 4.5% as well. The objective is to find out level of service C, but D is also acceptable. Okay, so the aim is to have level of service C, but for some reason if you settle down for D, it's acceptable. Okay, so in this analysis, as we have done previously as well, we always start with what? Free flow speed. Okay, free flow speed for freeways. Okay, so I need 3 things. One of them is given. Which one? Ram density is given. FLW is factor for lane width. Is the lane width given? No. FLC is a factor for lateral clearance. Is it given? No. So what should I do? Assume what?
Number of
The answer is correct, but what should I assume? Any value? 2 feet, 3 feet, 50 feet.
the given standard.
Standard, right? If I have to assume when I'm designing, I should assume what? The standard. Make sense? Huh? Somebody gives you a design, you don't know anything, you follow the standards. Very simple. Okay? Engineering, very difficult. Actual design, very simple. Okay? I don't know anything, I'll follow the standards. Clear? Okay? So standard lane width is 12 feet, standard letter clearance is 6 feet. Okay. What does standard mean, or why I'm saying these are the standard values? Look at the table for FLW, 12 feet. Factor is
0.
Okay, that's why I'm calling it the standard. It's written somewhere else that this is the standard, don't worry. In the same book, it's written somewhere else that 12 feet is standard. But if you don't remember, you just come to the table and see which value has a factor of 0. That's it. Okay, same thing with FLC. We don't remember the values, just look into the table. Whichever value makes a factor 0. Okay. So give me the free flow speed, just TRD has to be plugged in. How much? 73.6 miles per hour. Okay, now for each type of analysis, the basic equation is different. Okay, in this analysis, the basic equation is I'm trying to find out n number of lanes. Okay, so this is GTHV divided by peak hour factor, MSF. Okay, MSF has subscript of I multiplied by FHV. Okay. Peak hour factor given. Right? FHV factor for what? Having fun. Huh? Having fun. So this factor requires a percentage of heavy vehicles, which is how much? 15%. Okay, and it requires EHV. EHV depends upon terrain. Now terrain has a problem here. What's the problem with terrain? What's the problem with terrain here? Only with grade. Huh? So it's not level with grade. Two different parts. So the segment has two different parts. One in a level terrain, the other one designed for a gradient of 4.5%. Okay, so it has both a level terrain and another 2 mile segment, because freeways are very, very long. You can go up to 10 miles, 20 miles, something like this. So terrain conditions do not remain constant. That's why we did the multiple gradients case earlier. It can happen. Okay, even if I have a gradient, I can have multiple gradients. Having multiple gradients, no problem. I can combine them into an average value. In this case, and I cannot. There's nothing combining level with a gradient, right? You cannot combine them. They have to be treated separately. So I will calculate 2 FHVs or 3. I calculate 3. One for level, one for, we did it last time as well, gradient, and the third one, upward and downward. One for level, one for upward gradient same, downward gradient same. Gradient is same, the direction will change. Okay, so it will change the EHV, right? It will change the EHV. So let me take the EHV first of all for level terrain. For level terrain, the EHV you can see here is 2. Okay, so if I put EHV as 2 and percentage of heavy vehicles 15%, how much is FHV? So FHV for level, EHV is 2 here. How much? 87. Okay, then FHV downward, looking at downward gradient is easier because of the table. Okay, for EHV I already showed you earlier a couple of times. We have this table and this one. This one is for standard mix. This one is for other 2 types of mixes. Okay, so we have the equal mix and the heavy mix. We have the heavy mix, right? We have the heavy mix. So I look into this one. Percentage of trucks 15%. Okay, if you cannot see the number, don't worry. Okay, I will tell you the number. If I go to the slideshow, it doesn't record properly. So, yeah, close lights, close door, close the campus, no problem. Just don't sleep. Okay, 15% trucks. Okay, downward gradient is this one. Okay, equal to or less than 0. So for downward, the value is 2.04. Okay, for downward gradient, the value is 2.04. Now for upward, I have to look for the value of gradient, which is 4.5% here, and the length is 2 miles. Okay, so 2 miles is here. More than 1 mile, right? So it comes out to be 3.11. So 2.04 for downward and 3.11 for upward. Okay, give me the FHV values now.
0.76.
Okay, now you can notice here that level and downward are same by chance. Got it? By chance. Because obviously EHV and EHV for level and EHV for downward are coming from 2 different tables. They have different values. Okay, so here it is coming by chance same. In some other case it can be different. Okay, so don't assume anything. Okay, if you have something like this, you need to calculate. Now since I calculated, I found them to be same, so I know I can combine them. So downward and level will be same. I'm not combining them, they are just same. Okay, so I will do one solution for level and downward case and the other solution for upward case. Clear? Okay. So I needed FHV, I found FHV. Now I need MSF, which is called as maximum service flow rate, and then you can see a subscript I here as well. I refers to the level of service. I refers to what? The level of service. Okay, so I need to find out maximum service flow rate at the required level of service. What level of service I require? C. I can go up to D. So I should find both. I should find both. Okay. There are two ways to do it. Okay. I'll tell you both of them. One way which you have to do for your term projects as well is to plot the speed flow curve. To plot the speed flow curve. Okay. I'll show you the speed flow curve. This is a speed flow curve you have to plot. On this curve, you already know one point, which is what? You know? Tell me. When we calculate, we know free flow speed. So I can draw this line, right? I can draw this straight line. Okay? This straight line will go up to breakpoint. Okay? For breakpoint, I have this equation. Okay? So I'll use this equation to calculate the breakpoint. Give me the breakpoint. The free flow speed was 73.8. As I mentioned yesterday as well, there are no adjustment conditions given, no weather condition given, no incident given, no work zone given. Driver population all familiar, they are saying. Okay, so even if the condition is given, it is standard. So no adjustments required. So free flow speed is what you have, and capacity adjustment factor is 1. Free flow speed was 73.8, right? Was it? 6? Yeah. 1056. Okay. Okay, so the breakpoint is 1056 passenger car per hour per lane. Okay, if I go back to the speed flow curve, so I will start from free flow speed 73.6. I'll draw a straight line till I reach 1056 here. So here I have 1056. Okay. Then the next point is what? Capacity, right? Okay. So I need to find out the capacity then. This is the equation for capacity. How much is it? Two four three six. But there's a limit. So you cannot go beyond this limit. So if it is 2436, I will take what? 2400. Okay. So this point is 1056 and this point is 2400 then. Can I draw the curve? We need more points.
Use this equation.
Yes, to calculate what?
The speed.
The speed. Okay. But before I use it for any other point, I need to calculate the speed at capacity. What will be the speed at this value? The y-axis, right? Capacity is what? The x-axis. So I need to find out the value on the y-axis. So in this equation, I will replace Vp. Okay, I will replace Vp with capacity. So I will get the speed which is at capacity. Got it? For the rest of the points, to draw the curve, I need more points. So I will replace some more values of Vp. These values will be selected by me as per my own choice. But they must be between what? They must be between the breakpoint and the capacity. So you cannot select Vp of 2500. Or you cannot select a Vp of 900. 900 is here and 2500 will be after capacity, which is not possible. Okay, so you have to select few more values of Vp between the breakpoint and the capacity. At all these values, you will do what? You will put those values in the equation and calculate the speed. So the value which you selected becomes your x-axis and the speed which you will calculate becomes your y-axis. Okay, so now how will you plot the curve? You will plot here 73.6, which is your free flow speed. You will draw a straight line till 1056. Okay, from 1056 till 2400, you will choose different values of Vp, put them in this equation and calculate what? Speed. Okay, and then once you have the x-axis value, the y-axis value, you will join all the points, you will get this curve. Understood? Any questions? Clear? Now I am drawing this curve to find out the maximum service flow rate for level of service C and D. Okay, after plotting this curve, I'll go to this table and find out what is the maximum density for C. How much is it? 26. And the maximum for D is 35. Okay, 26 and 35. To plot, so I'm looking for these lines. When I plot these lines, wherever these lines intersect my curve, that becomes my maximum service flow rate. Okay, so what I will do, let me show you the curve now, what they have plotted. Okay, so this is the free flow speed, this is the breakpoint, this is the capacity. These are some more values which they have taken between the capacity and the breakpoint, and they plotted the curve. After that, this is a line for level of service C. This is a line for level of service D. Level of service C has a maximum density of 26 and D has a maximum density of 35. Okay, so what do you do with 26 and 35? You take the inverse, and the inverse of density becomes the slope of the line. Okay, so what is the slope of this line? It is inverse of 26. Okay, and what is the inverse of this line? It is inverse of 35. Got it? So you already have the curve. Then you found the slope of the lines and you plotted the lines for C and D. For your project, you have to plot for A, B, C, D, E. Okay? If you do it for F, you will get extra marks. Okay? So wherever the lines are intersecting, so you see the line is intersecting the curve here and here. So this is the line for level of service C, This will give you maximum service flow rate of C. This is a line for level of service D, so this will give you maximum service flow rate of D. Clear? And these are the values 1747, 2108. Okay? Which of these values I am interested in? C, right? I'm interested in what? C. Okay, so I will take for the time being the value for C, which is 1747. Okay, and the calculation is already done here. This is DDHP, this is peak hour factor, maximum service load for C, and 0.87 is the FHV. This is for level, which is the same as downward. Okay, there's a small difference in fractions, no problem. It will not create much difference here. Okay, and this is for upgrade. So you see when I do it for level and downgrade, I get 2.09 lanes, and when I do it for upward gradient, I get 2.39. Okay, so one lane is how many feet? One lane is how many feet? What did we say? 12 feet, right? We said we assume a standard. Okay, so 12 feet one lane, 12 feet one another lane, and 0.09. What do I do with 0.09? What? Why are you laughing?
Because no.
Huh? There is no answer. So how many lanes I provide? Two? Two? Why two?
Three.
Three. Three. Okay. The logical thing is to provide 3 lanes. Okay. Because 3 lanes will suffice for all conditions, right? So it's consistency as well. You have consistency. That level and gradient portion, everything has 3 lanes. So this is more than what we require, and it will have consistent design as well. Okay. But they said, the client says, no, I have a problem at the site, I cannot provide more than 2 lanes, I don't have a space, or it will cost me more, right now I don't have the budget. Okay, so we make 2 lanes. Now what will be your answer? Throw everything into his face and say, take your college, don't want to do it. Right? What would you do in that case? If he insists on providing 2 lanes, what do you do?
We check if it's level of service D.
Yeah. C, we know. C will not be maintained, right? If he provides less than this, it's not C, I know that. Because I calculated them for C. Okay? So now, in the same equations, you can put MSF of D and check. If you get a number of less than 2, then providing 2 lanes, you tell him, okay, you provide 2 lanes, you will maintain level of service D. Simple. Got it? Clear? You put MSF of D and 2 still does not satisfy that, and even with D you are getting more than 2. And you say, okay, even your minimum will not be satisfied. Got it or not? Clear? Any questions? Okay, but providing 3 lanes, I already told you, is that it has the advantage that everything will be consistent. Number of lanes will be consistent, and one more advantage is for the future, or if you made any error in calculating your volume. So if your design volume is more than expected, or in future the number of cars will increase more, number of vehicles will increase more, so 3 lanes will still maintain level of service C, even with more cars or with less accuracy in the prediction. Got it? Got it? Clear? Any questions? Okay. Yeah. So this is one method, no? Drawing the curve and so on and so forth. So we draw the speed flow curve, find out the MSF, right? Another method is this one. Okay. So in this method, they are saying speed equals to what? Flow rate upon density, right? Speed equals to flow rate upon density. Do I know the density for each level of service?
Yes.
I know it, right? So instead of using the speed equation and then drawing the curve and then finding out the maximum service flow rate, I can replace speed with flow rate upon density. So density I already know and I already have the equation. So I will find from this equation what? Flow rate. And since I am using the density of C, so I will find out the flow rate for C. If I use the density of D, I will find out the flow rate for D. But there is a small issue here. This equation only works when you have seen the speed flow curve, right? It's here. This equation only works where? In the curve or in this graph. It only works where? After the breakpoint. Okay? So if you are using this equation on level of service C and D both, that means you are saying C and D both are after the breakpoint. We don't know. Do we know this? I don't know. You guys know I don't. I'm sure. Right? But this is the small issue with using the equation, that we are assuming by using this equation that my flow rate is after the breakpoint. Clear? If it is before the breakpoint, then it's very easy that we know speed equals to free flow speed. Okay? So you can even use that as well. Anyway, if you plot the curve, it works for everything, right? If you plot the curve, it works for A and B and C and D and E. It works for everything. Okay? You can find intermediate values as well. Okay? You want to check other levels of service? No problem. You can even do reverse calculation as well. Put 2 lanes here. Put 2 lanes here and see how much flow rate you are getting. Then check the curve. So plotting the curve works in every way. Okay? So this method is easy. You don't have to plot the curve and so on and find out the breakpoint and everything. But there's the problem. Okay? Clear? Okay. Next example is for the growth rate. Okay, we have a 6-lane urban freeway. Free flow speed is measured already. Free flow speed is measured. 65 miles per hour. It has rolling terrain. Okay, 10% trucks, standard mix. Okay. Other standard conditions apply, so there is no CAF and SAF. What is this? What is CAF and SAF? Capacity adjustment factor, speed adjustment factor. So no requirements. Peak hour factor is given, traffic volume is given, current in one direction. Okay, as always. This volume will increase by 6% every year for the next 20 years. So the growth rate, annual growth rate for the next 20 years is 6%. So they are asking for what is the level of service now, after 5 years, after 10 years, after 15 years, after 20 years. Okay? So we calculated level of service in 2 examples yesterday, right? You can do the same method here as well. But you will do it multiple times. You have to do it multiple times. One for current year, one for 5 years, one for so on and so forth. Okay? And each year you will change what? The volume will change. Okay? So let us see how the volume changes. Now, if 6% every year, then how much after 5 years? Mm-hmm. 6% every year, 5 years, 2%. Very good. Huh? 30%. This is what they thought in the ministry. Huh? Who was with us in the site visit? No one from here, right? No, not today. Sunday's site. So they were saying they are from UOB. Okay. So the problem is when you say 30%, you are saying that every year it will increase 6% of this volume, the current volume, which is not the case. After year 1, the volume will increase by 6%, right? So next year, it will be 6% of the new value, not the existing value. Got it? No? What is the value now? No, what is the volume now? Volume. 3,600, right?
Yes.
Next year, it will not be 3,600. It will increase by 6%, right?
Yes.
So the year after that, it will increase by 6% of what? This?
No.
No, the new one.
New.
Okay, so when you say 30%, you are assuming that it is 6% of this value every year, which is not the case. Okay, so it's 6% of the new increased value every year. So in that case, we apply the concept which is known as a compounding growth rate, where future value equals present plus 1 plus the growth rate to the power, where is it? N, where N is number of years. I is the growth rate, N is number of years. Now everybody is saying, yeah. We already knew this. Okay, give me the value. P is current. Give me the value for 5, 10, 15 and 20 years.
4818.
So F5, how much?
4818.
4818 vehicles per hour. F10, 6447. F15. F15 is an airplane.
8628.
Okay, F20.
11546.
Any problem till here? Clear? So you can apply the same procedure which we did yesterday for the freeway, but the good thing here is I don't need to calculate free flow speed. It is given. It is given. Okay. But if you applied that procedure, you have to do it multiple times, right? Every time you will change the value of V and do the entire thing again. Okay. There's another method. Just for the sake of practice, we will do that by the other method. But if somebody did it from the yesterday's method, calculated level of service for current year and 5 years and 10 years using the same method, no problem. It's not wrong. Okay, but we are just looking at another method. Okay, so that you guys keep, I keep you confusing. Okay. So in this method, what we will use is the maximum service flow rate. In the previous example, the design example, we draw the curve, right? We draw the curve and find out maximum service flow rate for C and D, and I told you you can do it for A and B and E, okay? And you will do it for your projects in this way. Using the maximum service flow rate, you should plot the curve. But my free flow speed is how much? My free flow speed is how much? 65. For 65, it is already given. So why not I use it? If I don't have to plot the curve, there's no extra work. So why not I use the given values? Okay. So for 65, the maximum service flow rates are these values. Okay. Okay. Okay, these are the values I'm looking for. Now, what was the definition of maximum surface flow rate? What does it show?
The maximum volume without changing, after that we will change the.
After that, we will change the level of service. Okay. So if my given value, my volume is under 710, then my level of service is A. If it is under 1170, it is under, or it is B, and so on and so forth. Okay. So I just need to compare. So see, now it becomes easy. I just compare two values. But can I compare this one, these values with this one? No. Why? Because of the units. These are volumes. These are flow rates in passenger cars per hour per lane. So I need to convert them into passenger cars per hour per lane as well. Okay. So to convert the volumes into passenger cars per hour per lane, or I can do the other way around. I can convert these into vehicles per hour. Either convert them or convert these. Okay. So let us convert them again, just for the sake of confusion. So we for converting volume to flow rate, we were dividing with peak hour factor, number of lanes, and FHV, right? For converting flow rate to volume, I will do what? I'll multiply. So all these values will be multiplied by peak hour factor, number of lanes, and what? What else? FHV. Okay. Peak hour factor given, right? Number of lanes given. FHV, I'll just calculate FHV. Okay. So FHV, we already know that FHV equals this.